Conclusion. By wielding infinity in just the right way, calculus can unlock the secrets of the universe. We've seen that happen again and again, but it still seems almost miraculous. A system of reasoning humans invented is somehow in tune with the harmony of nature. It's reliable, not just at the scales where it was invented, at everyday scales of ordinary life, with its spinning tops and its balls of soups, but also at the smallest scales of atoms and at the grandest scales of the cosmos, so it can't just be a tree of circular reasoning. It's not that we're stuffing things into calculus that we already know, and calculus is handing them back to us. Calculus tells us about things we've never seen, never could see, and never will see. In some cases, it tells us about things that never existed but could if only we had the wit to conjure them. This is, to me, is the gateway mystery of all. Why is the universe comprehensible, and why is calculus in sync with it? I have no answer, but I hope you'll agree it's worth contemplating. In that spirit, let make that you let me take you the twilight zone for three final examples for the airy effectiveness of calculus. Eight decimal places. The first example takes us back to where we started with Richard Feynman's quip the calculus is the language God talks. The example is related to Feynman's on work on an attention of quantum mechanics called quantum electrodynamics, or QED for short. QED is the quantum theory of how light and matter interact. It makes Maxwell's theory of electricity and magnetism with Heisenberg's and Schrödinger quantum theory and Einstein's special theory of relativity. Feynman was one of the principal architects of QED, and after looking at the structure of his theory, I can see why he had such admiration for calculus. His theory is chock full of it, both in tactics and in style. His teaming with power series, integrals, and differential equations, and includes plenty of hitchings with infinity. More important, is the most accurate theory anyone ever devised about anything. With the help of computers, physics are still busy summing the series that arise in KD using what are known as Feynman diagrams to make predictions about the properties of electrons and other particles. By comparing those predictions to extremely precise experimental measurements, they've shown that the theory agrees with reality to 8 decimal places better than one part in 100 million. This is a fancy way of saying that the theory is essentially right. It's always hard to find helpful analogies to make sense of such big numbers, but let me try putting it like this. 100 million seconds equal 3.17 years. So getting something right to within one part in 100 million is like planning to snap your fingers exactly 3.17 years from now and timing it right to the nearest second without the help of clock or alarm. There's something astonishing about this, philosophically speaking. The differential equations and integrals of quantum electrodynamics and equations of the human mind. They are based on experiments and observations. Certainly, they have reality built into them to that extent. Yet they are products of the imagination nonetheless. They are not service imitations of reality. They are inventions, and what is so astonishing is that by making certain scribbles on paper and doing certain calculations with methods analogous to those developed by Newton and Leibniz, but sum up. For the 21st century, we can predict alternators in most properties and get them right to 8 decimal places. Nothing that humanity has ever predicted is as accurate as the predictions of quantum electrodynamics. I think this is worth mentioning because it puts the lie to the line use something here that science is like faith and other belief systems, that it has no special claim on truth. Come on, any theory that agrees to one part is 100 million is not just a matter of faith or somebody's opinion. It did not have to match 8 decimal places. Plenty of theories in physics have turned out to be wrong. Not this one. Not yet, at least. No doubt it's a little bit off, as every theory always is, but it sure comes close to the truth. Summoning the positron. The second example is the airy effectiveness of calculus has to do with an early extension of quantum mechanics in 1928. The British physicist the British physicist Paul Dirac tried to find a way to reconcile Einstein's special theory of relativity with the governing principles of quantum mechanics as applied to an electron moving near the speed of light. He came up with a theory that struck him as beautiful. He chose it largely on aesthetic grounds. He had no particular empirical evidence for the theory, just an artistic sense that its beauty was a sign of its correctness. Those constraints, those constraints alone, compatibility with relativity and quantum mechanics, along with mathematical elegance, tied his hands to a large extent. After starting with various theories, he found one that matched all his aesthetic desiderata. The theory, in other words, was guided by a quest for harmony, and like any good scientist, Dirac sought to test his theory by extracting the predictions from it. For him, as a theoretical physicist, that meant using calculus. When he solved his differential equation, now known as the Dirac equation, and kept analyzing it over the next few years, he found that it made several startling predictions. One that antimatter should exist. There should be, in other words, a particle equivalent to an electron, but with a positive charge. At first, he thought that particle might be a proton, but the proton had too much mass. The particle he predicted was about 2,000 times smaller than a proton. No such positively charged particle that wispy had even been seen, yet his equation was predicting it. Dirac called it an anti-electron. In 1931, he published a paper in which he predicted that when this still unobserved particle collided with an electron, the two would annihilate each other. This new development requires no change whatever in the formalism when expressed in terms of abstract symbols. He wrote, and he added dryly, under these circumstances one would be surprised if nature had made no use of it. The next year, an experimental physicist named Carl Anderson saw an odd track in his cold chamber when he was studying cosmic rays. Some sort of particle was crawling like an electron but curving in the opposite direction, but as if it had a positive charge. He was unaware of direct prediction, but he got the gist of what he was seeing. When Anderson published a paper about about it in 1932, his editor suggested he call it a positron. The name stuck. Dirac won a Nobel Prize for his equation the next year. Anderson won the positron in 1936. In the years since then, positrons have been put to work saving lives. They underlie PET scans. PET stands for positron emission tomography, a form of medical imaging that allows doctors to see regions of abnormal metabolic activity in soft tissues in the brain of the other organs, in a non-invasive fashion that requires no surgery or other dangerous intrusion into the skull. PET scans, PET scans can help locate brain tumors and detect the amyloid plaques associated with Alzheimer's disease. So here's another sterling example for calculus as the handmaiden to something marvelous, practical, and important. Because calculus is the language of the universe as well as the logical engine for extracting its secrets. Dirac was able to write down a differential equation for the electron that told him something new and true and beautiful about nature. It led him to conjure up a new practical reality that it ought to exist. Logic and demanded it, but not on their own. They had to align with known facts and mesh with known theories. When of the fact was stirred into the pot, it was almost as if the symbols themselves brought the positron into existence. The mystery of comprehensive universe. For our third example of the early effectiveness of calculus, it seems appropriate to end our journey in the company of Albert Einstein. He embodied so many of the themes we've touched on: a reference to the harmony of nature, a conviction that mathematics is a triumph of the imagination, a sense of wonder at the comprehensibility of the universe. Nowhere are these themes more clearly visible than in his general theory of relativity. In his theory, his magnum opus, Einstein overturned Newton's conceptions of space and time and redefined the relationship between matter and gravity. To Einstein, gravity was no longer a force acting instantaneously at a distance. Instead, it was an almost palpable thing, wrapped in the fabric of the universe, a manifestation of the curvature of space and time. Curvature, an idea that goes back to the birth of calculus, to the ancient fascination with curved lines and curved surfaces. In Einstein's hands, become a property not just of shapes, but of space itself. It's as if the XY plane of Fermat and Descartes took on a life of its own. Instead of being an arena for the drama, space between an actor in its own right. In Einstein's theory, matter tells space-time how to curve, while curvature tells matter how to move. The dance between them makes the theory nonlinear, and we know what it means. Understanding what the equations imply is bound to be difficult. On this day, the nonlinear equations of general relativity conceal many secrets. Einstein was able to excavate some of them through his mathematical skill and doctness. He predicted, for example, that starlight would bend as it passed around the sun on its way to our planet, a prediction that was confirmed during a solar eclipse in 1919, and that made Einstein an international sensation, front page news in the New York Times. The theory also predicted that gravity could have a strange effect on time. The passage of time could speed up or slow down as an object moves through a gravitational field. Bizarre as this sounds, it really does occur. It needs to be taken into account in the satellites of the global positioning system as they move high above the Earth. The gravitational field is weaker there, which reduces the curvature of space and time and causes clocks to run faster than they do on the ground. Without correcting for this effect, the clocks about the GPS satellites wouldn't keep accurate. They get ahead they get ahead of ground-based clocks by about 45 microseconds per day. That may that may sound like much, but keep in mind that the whole global positioning system requires nanosecond accuracy to work properly, and 45 microseconds is 45,000 nanoseconds. Without the correction for general relativity, errors in global positions would accumulate at would accumulate at about 10 kilometers each day, and the whole system would become worthless for navigation in a matter of minutes. The differential equations of general relativity make several other predictions, such as the expansion of the universe and the existence of black holes. All seem outlandish when they were predicted, yet yet all have turned out to be true. The 2017 Nobel Prize in Physics was awarded for the detection of another outrageous effect predicted by general relativity, gravitational waves. The theory showed that a pair of black holes rotating across each other or would swirl the space-time around them, stretching it and squeezing it rhythmically. The resulting disturbance in the fabric of space-time was predicted to spread outward like a ripple moving at the speed of light. Einstein doubted that it would ever be possible to measure such a wave. He worried it might be a mathematical illusion. The achievement of the team that won the Nobel Prize was to design and build the most sensitive detector ever made. On 17, on September 14, 2015, the apparatus detected a space-time tremor 1,000 times smaller than the diameter of a proton. For comparison, that's like tweaking the distance to the nearest star by the width of a human hair. It's a clear winter night. As I write these last words, I step out to look at the sky. With a star up above the blackness of space, I can't avoid feeling away. Oh, how could we, Homo sapiens, an, an insignificant species on an insignificant planet adrift in a Middle Way galaxy, have managed to predict how space and time would tremble after two black holes collided in the vastness of the universe a billion light years away. We knew what, what the wave should sound like before it got here, and courtesy of calculus, computers, and Einstein, we were right. That gravitational wave was faintest whisper ever heard. That soft little wave had been headed our way from where we were before we were mammals, for a time in our microbial past. When it arrived the day in 2015, be, because we were listening and because we knew calculus, we understood what the soft whisper meant.